All right, so as an algebraic geometer, we're interested in the geometry of algebraic varieties. And the first type of algebraic variety that we want to study is a projective variety over algebraically closed field. And there are many interesting stories about those varieties. But from Murray point of view, we should study rational curves inside on a projective variety. To be more precise, we want to consider maps from a P1 to our variety X. An interesting case of a variety, an interesting case. Our variety X with many rational curves. So we want to be more precise about many rational curves. What does that mean? So here is a definition that a variety has many rational curves. So X is called separately rationally connected. I use SRC, stand for separately rationally connected, if there exists a family of maps such that, first, this family is a family of rational curves. And we consider the two evaluation morphism. This one is separately dominant. So this means that if X is your variety, and you can pick up general 2 points, and then this one is dominant, says that there is a rational curve through these 2 points. And in characteristic 0, we don't even need the separate. It's just a dominance. Okay, so this is a good notion of a variety with many rational curves, because the variety itself are spread out by rational curves. But this is not a good definition in the sense that if you want to check something is separately rationally connected, then you always need to cook up a family, and cook up a family could be very painful. So here, so the next one is a better definition. So let's introduce a morphism from P1 to a variety. This one is called very free. If pullback of the tangent bundle is M. And then if you want to check something is SRC, it's sufficient to, it is necessary and sufficient to verify that there exists a very free rational curve. So the key point to prove something is SRC is really construct a very free rational curve. this is really a beautiful theory in the sense that we have nice definitions and we have many interesting examples. So, so the important example proved by Mori is that if you consider a smooth funnel variety over a characteristic 0, and then these varieties are all rationally connected. Here I don't need separately rationally connected because over characteristic 0, every morphism is separate. Okay, so this is a really an important example, provide a large class of rationally connected varieties. And there are important arithmetic applications. For varieties, over function field of curves. So f, this is a function field of curves over, for example, complex field. So one important example is we could consider if a geometric fiber of this one is rationally connected, then this implies that the original variety over the non-closed field has many rational points. So this is a famous theorem of River-Hardy-Starr. And for number theories, they not just consider existence of rational points. They also consider approximation problems. Indeed, rational connectedness implies, I put this, implies weak approximations. So this means that sometimes I do not just I'll need some other conditions together with rational connectedness that will imply a weak approximation for a variety over a non-closed field like F, function field of curves. So there are many interesting works on this by Hassett, Chico, Delon, Starr. So I don't want to define what a weak approximation right now, because I'll go back to this problem later on. So, so we are happy with projective varieties, because one of the reasons we're happy with it is because it has so many interesting theories and so many interesting applications. But projective varieties are not the only varieties we started. For example, the first variety I learned in density algebraic geometry class is affine variety, spec R, which is not projective. So we might just want to say something about those varieties as well. Okay, so so let's start with a quasi-projective variety. Again, I want to start with geometry. So following Mori, then we would like projective. We would like a rational curve inside this. Okay, but sometimes this one might not have a whole projective, whole rational curve, because, for example, this is an affine curve. It cannot have a whole P1. So most of the time we just have a rational map. But there are two important curves inside the quasi-projective variety. The first one is like before, we could have a whole rational curve, but this not always exists. And the other possibility is, the other interesting case is we don't have P1, but we have P1 without just one point. So it's A1 inside our quasi-projective variety. And I want this one to be a proper model. And so for this talk, we're going to focus on this stage, on this case. And indeed, I should mention that, so to study A1 curves in quasi-projective variety already has a lot of evidence. Why should we do that? From the work of Miyanishi, Hugh McKinnon, and Campana, we already see a lot of important things why we should study A1 curve rather than C star curve. It's because the way that A1 curve inside the quasi-projective variety behaves more like a rational curve inside your projective variety. Okay, so then we can just mimic the case of rational connectedness. We can make sense of what does it mean a quasi-projective variety with many rational curves. So the definition is a quasi-projective variety X is separately A1 connected. I use SAC if there exists a family such that the three conditions hold. First, I want families of A1s. And second, I want each fiber gives you an A1 curve just like this case. And third, I want the evaluation morphism, the two evaluation morphism. Is separately dominant. Okay? Separately. So okay. So from the definition, it seems that these are really parallel geometry, and they are quite similar to each other. But later we will see in examples they're very different. And if you want to start somehow the case of A1 curves, that gives you more delicate geometry that I need to consider. So So just like the case of rational connectedness, if you want to check something that is rationally connected, it's not so convenient to directly hook up a family with such properties. Instead, you want to construct just a map from a curve that satisfies this emptiness condition. So there are similar definitions in the case of A1 connectedness. So let's consider an A1 curve maps to my quasi-projective variety. There is a unique way of compactifying the A1. Namely, I just add the point at infinity. But there are many different ways of compactify your quasi-projective variety. But here I want to consider a compactification in such a way that this is what we call log smooth. Or equivalently, this is a toroidal compactification. So that means at tau locally, the boundary looks like a toroidal boundary. So that's the meaning. And if you don't like toroidal, just think of this as a normal crossing boundary. Okay? And then because this is a proper map, so this one extends. That gives you a morphism of pairs. By that I mean you have a morphism from P1 to X underline, and you have infinity maps to the boundary partial X. So now the definition that we're going to use is F between the pairs is called very free. If this time instead of the tangent bundle of your variety, I want to consider the log tangent bundle. So I use this. So log tangent bundle is just a subsheaf inside your tangent bundle where the tangent field has zeros along the boundary. So I want the pullback of the log tangent is n. Okay. So then like the case of rationally connected. So if we want to show that this time, instead of considering a quasi-projective variety, I would like to consider pairs. And so if the pair is A1 connected, is SAC, I just need to verify that there exists a very free A1 curve. So a very free A1 curve is a map of pairs from P1 with one marker point to this pair such that the infinity goes to boundary and the rest of that goes to the interior. This
a very free A1 curve, you could have many different very free apps.
Oh yes, the compactification, we just chose one compactification such that it's log smooth. But this one, but the definition itself is intrinsic to the projective the quasi-projective variety. It doesn't depend on the choice of your compactification. So for example, over character 0, we have resolution of singularities.
Why do you say that it has something to do with the algorithm? You're not making an assumption that your original variety, the interior is affine.
Say that in your question.
You're not making any assumption that the interior is affine or something, but it could send infinity into the interior as well, right?
Yeah, but I'm focusing on A1 curves right now. I really want this morphism to be a proper morphism. So if you extend your morphism like this, infinity goes to boundary. Any other questions? Okay. So here I want to mention that so the K-point, so a very useful tool study A1 curves inside your projective variety is by taking compactification. And there is an existing theory studying these things called stable log maps tool. Developed recently by Siebert, Stephen Martin, and Jonathan Weiss. So there are many recent works set on the foundations for stable log maps so that we can use this to study maps of pairs and its degeneration that becomes very useful to construct A1 curves. Okay. So like in the let's recall the case of rational connectedness. It's important, it's beautiful because it has nice examples. The examples are Farmer varieties, smooth Farmer varieties over characteristic 0. They are all rationally connected varieties. So a natural question to ask is if log Farmer varieties are separately A1 connected over characteristic 0. So unfortunately, this is not the case. So bad news is that log Farmer. This means i.e. The log canonic bundle is not NTM. It is NTM. This thing is ample. Plus log smooth plus characteristic 0 does not imply A1 connection. So to see a counter example, we can take the most naive one. So let's take X to be the projective plane with boundaries given by 2 lines. And this one is not A1 connected. So the reason for that is we know that an A1 connected variety, the open parts, namely your variety, indeed the boundary, always have finite fundamental groups. But this one has infinite elements in the fundamental. So this cannot be A1 connected. But this is a log fundamental variety. So it's not true that a log fundamental variety implies A1 connectedness. But this does not mean that A1 connectedness is an empty theory. We still have many interesting examples. So I want to tell you some interesting examples. some of the examples that I deal with E. So, so the first example that I want to talk about, actually the first, if you think about the rational connected varieties, the first example of rational connected variety are projective space, because any point are joined by a line. So for separate, so for A1 connected varieties, the first natural example is affine space, because affine space, any 2 point of affine space are connected by a line. But this one has a natural compactification given by projective space with a hyperplane. Of course, this one is A1 connected is not our, anyone can observe this. But the point is, this one is the only law smooth variety with positive changing moment. So if you have some log varieties, non-smooth variety with positive changing moment, it must be this. And this is indeed an analog of Harshman's conjecture for projective space, proved by Mori. And we have many interesting examples in the homogeneous situation. So if you consider G, which is a semi-simple linear algebraic group, we can consider its wonderful compactification. Yes? Okay.
Press hard.
Oh, okay, okay. So X, this is a compactification, toroidal compactification of G, indeed a wonderful compactification. So wonderful compactification of G. Then X is SAC if the characteristic does not divide the fundamental group where T is a maximum torus of G. So in particular, we say that if G is a if G has trivial fundamental groups, then it's SAC for arbitrary field, for a field of arbitrary characteristics. Okay. So this is a homogeneous example, and there are non-homogeneous examples.
Excuse me, are you adding the characteristic and the pi one? You mean the rank of the pi one?
Pi one of the, so this one is defined by, you take the character.
No, it's a slash, but the ambition side.
Ah.
Not divided.
Does not divide. Okay. Okay. Okay, so what about the non-homogeneous situation? So let's consider the case X. So this is a what we call smooth complete intersection in projective variety. So of type U1 through EC So this means that X underline is a complete intersection type of D1 through DC in Pn, and the boundary of X is another smooth divisor inside X underline cut out by a degree DD homogeneous polynomial. So here is what we have. So if this is log final, so this means then actually I'm using one important condition, which is the characteristic does not divide the degree of the boundary. So this also gave you many interesting examples. But no matter the case of simple linear algebraic groups or the case of smooth complementary intersection pairs, they are both the log final cases. Okay. So if we want to find a large class of A1 connected varieties, clearly log final is a pool that we want to study. But what are the other conditions we need to input so that we get to get a sufficient condition for A1 connectedness? This seems to me a very difficult but very interesting question. But luckily we do have a nice answer in the dimension 2 case. I forgot to mention that in dimension 1 case, there's only one case. So there is a nice result of E2. Says that let's consider X. So this is a log smooth surface. Then the following are equivalent. So X is log RC. So this means that exists either a very free P1 or very free A1. And second, the Itaka dimension of the pair is negative infinity. But this is not enough. We need the vanishing of pluriforms. And you can have an easier condition to determine A1 connectedness by only check few terms, not all M. So this doesn't like the case of smooth projective surfaces, where if it's final, if you have negative Cordero dimension, then you already have rational connectedness. Here we facilitate the conditions coming from this part. So, so natural question to ask is how those pluriforms are related to A1 connectedness. This seems a very interesting question. This, yeah, this is over characteristic 0. Okay. So, so far, these are all the examples that we have for A1 connectedness. But I think it's already interesting enough, and this certainly is not an empty theory. So, so what about the applications of A1 connectedness?
Is there a relation between rational connectedness and some non-Bayesian conformal like criteria coming from the
So you are talking about the analog of symplectic rationally connectedness for
you want some 2-point probability center, you want some extra minimizations for the
yeah, I guess there must be.
like this known or?
We haven't go to that part, but I think there are some things.
That's
Follow
not
this
known
one.
in the non-log case. Why are you asking about it in the log case?
What in the log?
I mean, the thing he's asking about, we don't know that in the non-log case. We don't know that in the absolute case.
Yeah, in lower dimension we do, right?
Oh, you're.
There are work of yours still, and
Yeah, but who wants to know in all dimensions?
I mean, homomorphic invariants in general are so difficult to calculate, even vary the non-vanishings.
No, the
It's kind of hard,
second part
so.
of my question is, if there is such a thing, then is this related to like a relative probability into 1 point, like tangent dimension, all like in related like 1 point or something?
Yeah, you can see that. I think you can see that. I don't have a proof of. Well, you notice the difficulty is here the boundary can be simple normal crossing, so the technique is going to be difficult.
Can I just ask, what was the result of Qile Chen? Because it's sort of related to.
Oh, yeah. I forgot to mention that Yizhu proved this beautiful result based on the previous work of Qile McKenna and Miyanishi. So, so Yizhu is here. You can ask him for more details. I mean, you need to run a linear model program, break it down to several cases, and analyze each.
I was just wondering, I think it was something like you take a log delta associative,
Mhm,
like
mhm.
a delta associative with singular points, and you use the singular points, that's A1 connected.
But there is one missing case.
I don't think you knew anything about that in the Python. Okay. Oh no, I think about it.
I wish I know that. But really beyond the surface case, that's the example we have. Okay, so just like the case that you have rationally connected variety, you can get beautiful arithmetic applications. You have A1 connected variety. You can also do something similar. So, so let me talk about arithmetic applications. Here I want to consider varieties over, again, a function field of curves. So here f is a function field of some curve B. Function field of over, let's see, complex numbers. So we want to study, in this case, integral points, and it's a weak approximation because this is a family of quasi-projective varieties, and we want to study strong approximations. So, so the first result is let's assume that this family assume that I have a compactification. So the first result is I want to mention is if we know that this thing is the geometric fiber are A1 connected and are geometric fiber A1 connected and geometric fibers are smooth pairs. So I want to consider a case that you have a variety over this non-closed field whose geometric fibers are A1 connected and they are given by the boundary is given by a smooth divisor. So in this case, so this implies Zariski density of S into a point. Where S is a non-empty set contains the place of battery actions. So, so I should mention that this is a work of Qile. And E and I basically restate this, figure out that we can actually restate this using A1 connectedness. So I just want to mention that what this means in an S integral point. So, so we have this general fiber, but you can realize this as an actual family over your curve B. And you have a boundary given by, generically given by smooth divisors. And there are some band reductions like this. And your S is a finite collection. Finite set, I should say. It's finite. It's a finite collection of points of a base curve B that contains all these band reductions. So an S integral point is a section such that its integral means it doesn't touch the boundary away from S, but it might touch the boundary somewhere here. Okay. Yes?
So, does S have to be finite?
S is finite, yes. Yeah. If S is infinite, then this Gruber-Harvey star, I guess, is weaker than Gruber-Harvey star. Okay, so but we are not only satisfied with integral points. We want to study, like in the case of rationally connected variety, there are results for approximations. And here we want to start with strong approximation. So so let's consider again a variety defined over this non-closed field. And now Now I want to talk about its strong approximation. So the result says that if this thing is a smooth complete intersection here of type B1, BC, BB in projective space. So that just means that the geometric fiber of this is going to be a complete intersection of type D1 through DC, and with a smooth boundary divisor covered by a homogeneous degree dB equation. So if I have a variety like this, if the degree bound is less or equal than n plus 1, then strong approximation holds. Yeah, I'm going to do that. Oh, sorry. I made an important mistake. So far we cannot do arbitrary dB. So we can only do this.
And the theorem is again with.
With usual, yes. So here. So what is a strong approximation? That's a fancier name for Chinese remainder theorem. So so we're going to prove some version of Chinese remainder theorem in this setting. So so what it says is I only want to state the geometric version of this. So we have this variety over this non-closed field. Now, I want to realize this in a family. So this is my base curve B, and I have an actual family with a boundary divisor. Now, there are several data that we need to associate to this family to state a strong approximation. So the first part is finite set S. S1, S2, you throw in whatever points that you don't like. The only criterion for this is it's not empty. So and we want another finite set. So those are points on your distribution. Another finite set T, T1, T2. So this set of points can be empty. But what we need is for each I, we want to associate the jet section, Ji. So what that means is you have a place Ti here. You take its infinitesimal neighborhood. So that means you take OB quotients MTI to some power And then you could base change your family to this infinitesimal neighborhood, and you want to associate a jet. That is a section. So this one is J I. And we want this further condition that band reductions. Namely, the set of points that whose fiber is singular is contained in the union S. So then, a strong approximation says that there exists a section from B to your family through all jets. And integral away from S union T is E. So that means away from S and T, this section does not touch a boundary. So then you can draw a boundary like this. Over band reductions, you might touch a boundary. And then you want to approximate your jets. So this is really a version of Chinese remainder theorem.
Don't you want some condition like that in every other place there exists a section? Like,
yeah, there is an infinitesimal section. For those places.
A selection of infinitesimal sections that you're fixing. And you also want to claim that there always exists infinitesimal sections in every place, right?
Well, over
Or is this a median?
He already proven that there are sections.
yeah, there are already sections. By Greber-Harris star, there. So A1 connectedness implies rational connectedness, and by Greber-Harris star, we already have rational points. But since we're dealing with quasi-projective varieties, the question is if we could produce integral sections that approximate the jet elements.
By the way, you said a fancy version of that
Is what?
Greber-Harris.
Okay, yeah. Okay, before I talk about the proof of this, I want to mention a corollary of this. So we know that this is what we know. If you have a smooth variety, which is RC, rationally connected, then this implies that there exists a rational curve from any finite number of points. In your variety X. So this is something that we already know for rationally connected varieties. And it's natural to ask the question that what if I just have a quasi-projective variety? Can I, if I give you a finite number of points, can you find an A1 curve through all those points? And we don't know the answer. But with this strong approximation results, we do have some examples that this holds. So with the intersection here in Pn of type satisfies a condition that the degree is bounded in such a way. Then
dB plus 1 or not?
can be arbitrary dB, as long as this inequality satisfied. So there exists a one curve through finitely many points in your quasi-projective graph. Okay, so this one is a consequence of strong approximation. Okay, so I have 5 minutes left. I want to just mention the proof. So our proof based on the known result of weak approximations from Hassett and Star. So step 1 is to notice that this family satisfies a weak approximation. So weak approximation says that if you forget about the set S, if you just fix a finite set with those jets, and then you could have a rational section that approximates those jets. So here I want to draw a picture again. This is my base D, and I have some jets, maybe in the on the boundary. So this is a result of I'm sorry. Actually, before step 1, there should be a step 0. Step 0 is even simpler. So as I just said, A1 connectedness implies rational connectedness. So such family definitely has a rational section. Okay. So this one has a rational section. So then let me draw a rational section. So we just choose one rational section. Let me see. Once we choose a rational section, the problem with this rational section is the rational section is going to hit the boundary away from the union of S and T. But that doesn't matter. So for example, this is a point that does not contain S union T. It doesn't matter. Because later on, we could throw in more jet conditions, forces the sections chosen from the weak approximation that approximates some interior point here. Okay. So the step 1 is to choose a section that approximates all the jets, and furthermore, it should pass through some integral points when the section from step 0 hits the boundary and that place is not in a unity. Now, So this step, we are starting space of A1 colonies. And to start in this space, we need a compactification. So we compactify that space of A1 colonies. We take a compactification using a stable log test. So the next thing about this space is it tells us that we could actually select a family of A1 colonies that swap out both section from step 1 and step 0. And okay, last step. So step 3 is the well-known result that strong approximation holds for A1. So since we already swap out both the jet and integral sections using a family of A1, now we just need to approximate jet over this family of A1, and that result is already known. So that's all what I want to say.
Are there questions for Qile?
So what if you instead of A1 you take A1 minus a point, then can you get something closer to log final?
That's a good question. Actually, in Kapana's program, you can put with boundary divisors, and so so in that sense, A1 is certainly a rational curve. You might have other rational curves, but it's 1, 2, 3 points, right?
Yes.
And in that sense, yeah, there are rational curves like that. But here I consider log canonical case.
But do you get something closer to log final?
Do you mean that if one can prove log final implies rational connectedness in that sense?
Yeah, in that sense, when you take A1.
I don't know. I don't think, did anyone know the result? I don't think anyone knows. But I could be wrong. So
But it sounds like good technology.
yeah, we're trying to using log consider some questions like that, but we don't have result yet.
If there are no more questions, let's thank Qile.